Hi guys, so I am taking this video to explain four things. Actually, first I will explain the installation of Iverilog, and then I will explain the installation of Visual Studio Code. Then I will explain the half-order circuit using Iverilog and the full and the D flip-flop using Iverilog. A person who has already installed Iverilog and Visual Studio Code can move to the further sections and doesn't have to see the first part. Thank you. Please use this to navigate through this video since it is a bit lengthy, and if you have already installed Iverilog and Visual Studio Code, you don't have to see the first part. Thank you. Hello guys, today I'm gonna show you how to set up how to install Iverilog on your computer. I have shared a drive link on the group, and in that I have put up the 64-bit setup file, and you can also find the 32-bit here. Like, depending on a computer, you can select the 64-bit or the 32-bit setup file. My computer is a 64-bit computer, so I am selecting this 64-bit setup, and you can right click on this and click on this download to download it. I have already downloaded it, and so here in my desktop folder I have this setup. I am just clicking on it, and this will ask for a permission, like you have to just provide yes to that. One second. It has asked for the permission and I have given a yes permission. Now the installation setup window will pop up. Here you can see the license agreement. You can read through it or not. After you have to click on this I accept the agreement and click on next. And this here you will see a warning which states that you have to select a destination folder without spaces. Like, if you can either choose the default location that Icarus is providing, that would be better. But if you want to change it, like if there is no space in the default folder, and if you want to change it, you can select a destination folder that doesn't have any spaces and click on next. This is just a warning, and here you can see this is the default location where Iverilog will be installed. You can change this by clicking on browse, but I prefer to keep it in the default location. You can change this by clicking browse, but make sure that you select a destination folder which doesn't have spaces in it and click on next. And after that, this step is really important. You have to click this full installation will be selected by default. You can keep it at you have to keep it at that, and make sure that these two options are checked, like install MinGW dependencies and install GTK Wave. Both are checked. Make sure that both these ones are checked. This is really important, and click on next. And here you can you can either choose to create like the setup will create a start menu folder which you can from where you can access this Icarus Verilog. It is completely optional. You can either choose to create or not create. I am choosing to create, so and click on next. And here you can see two options. Like, the first one is completely optional. You can either choose to create a desktop shortcut or not, depending on whether you access your software from desktop or not. Like, I will create one, and you can but this step is compulsory. The second one is compulsory. You have to make sure that this is checked. Add executable folders to the user path. This is completely compulsory. You have to make sure that this is checked, and after making sure that this is checked, click on next. And after that, you will get a prompt like ready to install, and then click on install, and this will start installing Verilog on my computer. And after this installation finishes, let me just wait it to complete installation. Now it has completed the installation, and after the installation you will get a window like this, and you can click on finish to make sure that it has installed. Okay, that's it. Hello guys, now I am gonna walk you through the installation of Visual Studio Code. In the drive link that I have shared earlier, I have in that you can find a folder called code editors, and in that code editors folder I have put in a folder called Visual Studio Code. I have put the installation file for both the 32-bit as well as the 64-bit. Mine is a 64-bit computer, so I am gonna right click on the 64-bit setup and download it, and click on download. I have already downloaded this file, and here it is. Like, it's in my desktop folder. I am just clicking on it. Like, here I can see the license agreement. I accept the agreement, click on next, and this is the default location in which Microsoft Visual Code would be installed. You can either change it if you want. I am just keeping the default location and clicking on next. This now it asks if you want to create a start menu folder. I want to create a start menu folder, so I am just clicking on next. And these are the additional tasks, like I'm just adding this. I just want it because I just want to open with code. When I right click, I can also want to create a desktop icon, so I clicked it too. Add to path is compulsory. You have to add to path. This, keep the default settings as if you wish. That's more better. Click on next and then click on install, and this will start the installation of Microsoft Visual Code on your computer. Now the installation has finished. Let us launch Visual Studio Code and click on finish. Now Visual Studio Code has opened up. Now one thing I want to show is you can click you can select the file like now in this desktop folder I have saved all the files that I require into this ICAR ICAR underscore files folder, and it's in my desktop. Now in Visual Studio Code I can open this folder by clicking on this file, and after that I can click on this open folder, or you can use the shortcut Ctrl K and Ctrl O. You have to press this simultaneously, and when I click on this open folder I will get a prompt like this. Here from this quick access or from this PC, you can select desktop. That's where I have stored the file. It might be a different directory for you. You might have stored it in downloads, or you might have stored it in desktop or documents or something like that. I have just stored it in desktop. I am just clicking on this iCar files and clicking on select folder. And now in my Explorer section, I can see this iCar files dot, all the files that I have in that folder I can see here. Now I can click on any text that I want. Now I will show you, for the first time I will show you the half adder, and when I click on this I can see the, and one more thing, like you can see that my code is colored, but initially your code won't be colored. So what you have to do is you can click on this extensions, and in this extensions you have to search for Verilog, and this you can have to click on I suggest that you install this one. This has over 258,000 downloads. Like I have already installed it. Like I will just when you first install Visual Studio Code and click on this extensions and search Verilog and select this. This is by MSHR hyphen H, and this has a downloads of 250. You can see like this, and this will be the format that you will see. Like for this I have already installed, that's why I am saying like this. And you can click on this install. Like I will just click on this install, and it will start installing for me. And after it's installed, you can also see the colors that I see when I open a file. And to go back, just click on this Explorer, and I can see all the files that I have there. Now let me just click on this half adder. Now you can see that the statements are colored accordingly. And this is the half adder module, and this is the half adder test bench circuit. Okay, now we have to simulate this. Now Sa has already provided a PDF which states the commands that you have to use to simulate a circuit. I am just gonna do this in Visual Studio Code. Okay, now you can see here that there is a terminal option here in the heading. You can click on this and click on new terminal, and what it will do is it will launch a terminal like this here. And what you can do is like it will automatically be navigated to the folder in which you have the file that's selected. Like I have this half adder underscore testbench.v selected, and this is the folder that I am in right now. So it will automatically navigate to the ICAR files underscore files that the current folder that you are in. And here you can type in the command prompt functions like ls to list all the files that are in this directory. A directory in command prompt language means folder. Okay, and in this ICAR underscore files folder, I have this many circuits which are the same as I can see here. So first we will as per SAS PDF, first we will compile To compile, this is the code, this is the statements that you have to use. You can either type in this whole thing or you can just type in this Iverilog. Both will work. And to make sure if your installation of a Verilog has successfully completed, what you can do is you can type in Iverilog here. Iverilog. The spelling the spelling and the case also has to be looked when you type this. Type in Iverilog and click enter. And if you let me just enlarge this. And if you see a prompt like this, then it means that you have successfully completed installing Iverilog. And what you can do now is to compile, you can type Iverilog -o my design and have, like there is an option now. As you can see in this files, there are let me just backspace. There are 3 files that starts by the name of HAL. Like I can type this HAL and I can click on the tab button on my keyboard to autofill. I don't have to type the whole file name. I just have to type some part of it, half HAL. Then I can click on tab. Then it will show me the first file. Like the alphabetic order, it will show me the first file. Then I click on tab once again. Then it navigates to the next one. Here I have 3 files that starts with HAL. So when I click on tab, it goes to the second file, it goes to the third file, then it repeats again. It goes to the first file itself. Okay, now I want the second file first. Then I will type in HAL, click on tab, then I get auto completed. Then I click on enter to compile this. And it has successfully compiled. And when we look at source PDF, you can see that the next step is simulation. To simulate, we can either write this whole code or you can just use this VVP. Now I'm gonna choose VVP and my design. Okay, and this has compiled and this has simulated my circuit. And now I am going to show you what these things mean. Like here you can see that in this half border test bench, you can see that actually what is happening. The inputs are T underscore A and T underscore B. Like input is A and B, like that. Here the input is T underscore A and T underscore B. And what are the different conditions that can exist for T underscore A and T underscore B? 4 conditions, right? T underscore A is equal to 0, T underscore B is equal to 0, T underscore A is equal to 0, T underscore B is equal to 1, and 0, 0, 0, 1, 1, 0, and 1, 1. And why are we writing this hash and 10? Like we are providing a delay. I will show you when the circuit is run and I will explain this that time. And one more thing you have to notice is you have to provide this $ dump file and this half adder underscore wave.vcd. This statement is meant to create a VCD file. Actually, .vcd files are required to get the waveform. Like the next step here is to type gtk wave and the name of the gtk wave half adder .vcd. To compile and all, you can use this .v file. But to get a GTK wave, you have to have a VCD file. So what this $dump file does is, it creates a file named half-adder_wave.vcd, and during the simulation type, it creates a file like this and dumps all the variables. This statement is just meant to create the file. And what this dump does this, it actually enters the values that are inputted, like TA underscore A is equal to 0. That's the first condition. This is the second condition. And for that you have to run the circuit, and all that is feeded into this file by this dump was command. So while doing future experiments, you make sure that you write these 2 commands to get the GTK wave output. Okay. And now that I have written GTK wave half-adder_VCD, dot VCD. I'm just clicking on enter, and this will launch the GTK wave. And here this is a thing we can use to see the output. And here this half-adder.tb is the module name. The test bench, like here you can see that we have created a half-adder dot underscore tb. That's the file name that we can see here. Now what we can do is we can click here, click on this. First selecting this, click on the first one, and pressing shift, click on the last one, and this will select all the things. Or you can select singly too. Like I am selecting all these ones and click on insert, and this will insert all the values into the waveform. As you can see, now all the values are 0. What is really happening is we have provided, I will told you that I will explain why this 10. One second. This GTK, what this happens is this 10 hashtag 10 is provided, this entered to provide a delay of 10 nanosecond, and what here is the scale is 1 picosecond, so we can't see the change. So to see that, you can click on this zoom fit, which automatically fits the waveform. And now as you can see, for the first condition, the statement begins here, t underscore a is equal to 0, t underscore b is equal to 0. That's the first condition. And as you can see, in the first condition, t underscore a is equal to 0 and t underscore b is also equal to 0. And here t, and what's the sum? This is a half-adder circuit, and as you can see, 0 plus 0 is equal to sum is equal to 0, and the carry is also equal to 0. Now after 10 nanoseconds, that is after we have provided a delay of 10 nanoseconds here, and after that what happens? T underscore a becomes 0 and t underscore b becomes 1. As you can see here, t underscore a is still 0 and t underscore b becomes 1. And what's 0 plus 1? The sum becomes 1 and the carry becomes 0. And after another 10 seconds, after another delay of 10 seconds, t underscore a becomes 1 and t underscore b becomes 0. As you can see here, t underscore a is 1 and t underscore b has become 0. And what's the output? Like what's the sum? 1 plus 0 is equal to, sum is equal to 1 and the carry is equal to 0. And after another 10 seconds, what happens is t underscore a is equal to 1 and t underscore b is equal to 1. And as you can see here, t underscore a is equal to 1 and t underscore b is also equal to 1. And the sum is 0, and like this 1 plus 1 is equal to 1, 0. So the sum is 0 and the carry is 1. And this is what is happening here. And this is the half-adder circuit. And this is how we use the Visual Studio Code and the terminal to. And after you have done with this experiment, you can just click on this close button, and this will end the terminal here, and you can close here, and you can make any changes. And after you have made any changes, you have to click on this terminal and start compilation from the start. You have to compile it, and then you have to stimulate. Hello guys, now I will walk you through the sequential circuit. Now I am going to explain the D flip-flop. And here you can see the D flip-flop module. Basic D flip-flop module is defined here. This Q and Q bar, and the D and the clock and the reset. And the two outputs are Q bar, and the inputs are D, clock, and reset. And what's happening here is when positive edge of the clock comes, you have to begin this, and what you have to do in this begin is if reset is equal to 1, if the value of reset is equal to 1, you have to give the value of Q as 0 and Q bar as 1, and you have to end it here. And if else statement, that is if reset is equal to 0, you have to give the value of you have to give Q the value of D and Q bar the value of the value of the complement of D, and it ends here. And that's the basic D flip-flop module. And the test bench, as you can see here, it is always hashtag 5. This gives the time period of the circuit, and this I will show you after I show you the waveform. And in the same procedure, what you have to do is you have to click on this terminal, click on new terminal, and what you can do is, and after this has loaded, you can just type in ls command to list all the files. Now we need to compile we need to compile it first. For the compilation, I'm just typing in Iverilog and my design 1, because I have already used my design for this half adder. I'm just using my design 1. Before that, I have to type in #o. And after this has loaded, I can just type in ls to list all the things. And to compile this, now we need to compile this. I'm just typing in Iverilog #o my design 1, because I have already used my design for this half adder circuit. My design 1. And what's the first thing? df test bench dff. I can click on tab to autocomplete. dff, and I can click on enter, and it has compiled the file. Now I need to stimulate it. For simulation, I can type in vvp my design 1. Don't type my design, it's my design 1. Click on enter, and this has, and what it has done is, as I have already said, it will create a simulation, and it will store the values into a VCD file. It will create a VCD file using this dump file command, and after that it will dump all these values that we want to enter by using this dump was command. And I will enlarge this right now, and as you can see, these are the different conditions. Reset is equal to 1. These are according to the specifications that we have given here. I will just explain in a minute with the graph. I can just type in GTK. To get the graph, I can just type in GTK wave and the name of the VCD file. The VCD file is dflipflop underscore wave.vcd. I can just write in dflip, click on tab to autocomplete, and then when I click on enter, it will launch the GTK window. Right now, it is launching. And here we are, and this is the name of the module. I can just click in there, and these are the different signals that are present in this module, like the clock input, the 3 inputs, clock, D, and reset, and the 2 outputs, Q and Q bar. I'm just clicking on shift, and after clicking on the first one, I'm just clicking on the last one to select all this, and now I am inserting it in the graph section. And as you can see, the scale is still 1 picosecond. I can click on the zoom fit, and it will automatically adjust my graph. 1 second, it is still adjusting. At that time, I will rearrange my slides. Okay, it has also rearranged. So now what we can say is, now in the initial condition, you can see that Q and Q bar both are undefined. What is really happening? So as you can see in this module of D flip-flop, Q and Q bar are first initiated at the first positive edge. Right. Here what happens is, after the D is equal to 0 and clock is equal to 0, reset is equal to 1. That's the initial condition. We haven't provided any initial conditions for Q and Q bar, and Q and Q bar are not declared here too, because the first positive edge hasn't reached yet. So Q and Q bar doesn't have any value in the initial condition, so they are undefined. They don't have any value, therefore they are shown as red. And then the first positive edge comes, and at the first positive edge, what are the conditions? Like the clock is at 1 and the D is 0, and the reset value is at 1. Reset value is at 1. So if you can see here that if reset value is equal to 1, this statements run. What is happening? Q is set to 0 and Q bar is set to 1. That's what's happening here. Here reset is equal to 1, and what happens at the positive edge? If reset is equal to 1, Q is set to 0 and Q bar is set equal to 1. That's what happened. And then what happens? At the negative edge, reset is set to 0. And here at the positive edge, reset is equal to 1, Q is set to 0 and Q bar is equal to 1. And at the negative edge, what happens? Reset is set to 0. And here you can see that at the negative edge, reset is set to 0. And then no change, it continues. the clock is at the negative edge, no change, therefore it continues. And then at the positive edge, normally what happens, the reset is equal to 0, and if reset is equal to 0, q will be set the value of d and q bar will be set the value of complement of d. Here d value is 0, therefore q will be given the value of what, the d, which is same as 0, and q bar will be given the complement of d, which is 1. And at the next negative edge, what happens? At the next negative edge, d is still 0, so d continues as 0, and at the positive edge, d is still 0, and therefore the same statement executes. Q is given the value of d and q bar is given the complement of value of d. Here the q is d value is 0 and the q value is therefore also 0, and q value is also 0 and q bar becomes 1. And at the next negative edge, d becomes 1. As you can see here, at the next negative edge, here the positive edge, and at the next negative edge, d becomes 1. And what happens is, at d remains 1 for the subsequent circuit. And what happens? At the negative circuit, d has become 1, because since it is a negative edge, no change takes place. And at the next positive edge, clock is activated and reset is equal to 0. What happens? Q is given the value of d and q bar is again given the value of complement of d. Here the value of d is 1, therefore the value of q becomes 1 and the value of q bar becomes 0. And since this value continues till this 55, you can see that since the value of d is 1, the q and q bar are given 1 and 0 respectively. And this is repeated, as you can see here, this is repeated 6 times at the positive edges. You can see the 6 positive edges here, 1, 2, 3, 4, 5 and 6. One second. And the 6 positive edges here, and it repeats until 10. Okay, thank you. And that's the flip-flop circuit explained. I hope it is helpful. Thank you.